So hello again, and now we should first discuss examinations. Christmas is drawing near, and that means that also the term is coming to its end. Now I have asked you to fill some questionnaire. I have received 13 replies, which is majority of students taking this course. So I hope that I have learned a little bit about your needs and expectations. And I would like to suggest two things. First, we will have examinations on Fridays. That is regularly, we would start at 9 o'clock and then have a written part of the examination. Then I will have some time to check your replies, and then we will continue by oral examination, and all of that will run through Microsoft Teams, except for the last term, which would be organized, if possible, also in normal way, I mean with people present at the examination. It seems that most of you are unable to come for a written part or oral exam to the Faculty of Electrical Engineering, which is now possible as to regulations for coronavirus, but still it's impossible to cross the border, for example. So I would expect that Microsoft Teams is most convenient for you. So this is the first point. The second point, some of you have asked me for a special term before Christmas because you want to go home, because you want to pass some examinations within the start of January, like the state exam, for example. Some of you are at the end of your studies. So then we would need to get a term in December, a kind of pre-term. Now this has got some advantages and disadvantages. The first, you will have to know all topics in electromagnetic field before the last lecture, so that I will have to examine also things that I have not lectured so far. So that's the first important point. The second point is that an examination is possible only you get assignments, započet, from Professor Machač. That's the rule of Czech Technical University, that the oral or written examination could only be provided to students who have achieved započet. So now we have to find out the date for this examination in December. Some of you have asked me for the 18th of December. From my side, it's possible. I would have the chance to organize this examination on Friday 18th, but you have to achieve započet before that from Professor Machač. Is that clear to everybody?
Yes.
Okay. Well then, if we have somehow known the playground, we can give other times or days for examination. So the preterm on the 18th of December would start at 10 o'clock, because I have some business before that. So for the preterm it is 10 o'clock, 18th of December. Now there will be regular terms, and I suggested them to take part on the 15th of January, 9 o'clock. Then, in 2 weeks, the 29th of January, again 9 o'clock. Then, on the 5th of February, again 9 o'clock. And the last term, the last Friday in the examination period, the 12th of February, again 9 o'clock. Now all of those are Microsoft Teams. This is for students that would be present here. Well, this is the plan. We do not know what coronavirus would cause by that time, so it might also happen that the last term would be in Microsoft Teams, but I will anyway leave some possibilities. So it might be combined between Microsoft Teams and students that are present. The first 3 terms are planned in Microsoft Teams only because it is somehow consistent with the prediction of coronavirus situation in this country, if there is any prediction that is valid at all. Is this clear to you?
Yes.
Yes.
Now I will make a special arrangement in order to prevent all students coming to the last term only. So those terms, the pre-term and those 3 terms, are free for anybody who has Započet. This term is available only to people that have already tried to pass the examination. So it's a reprobation term. So if you want to get this term, you have to try it at least 1 time earlier. Is that clear? Unless there is a special condition like illness or something like that. But I do not want all students to come only to the last term, because then it's long, stressing, and so on. So I would, and of course you should try to pass the examination earlier also to know all my demands. It's not a good idea to come on the last day when we have no boundary conditions to move anything. It's pass or die, and that's not a good situation. So I like to limit the last examination to those who have already tried to pass the examination earlier. So we have, in fact, we will have 5 terms for some 20 students or 18 students, which makes them a convenient distribution that should not last very long, because we will be able to go on. Now a special arrangement for Microsoft Teams examinations. So you should have your computer and internet connection available for the whole time of the examination. You should have your camera on. I will send you the tasks and questions through Microsoft Teams at the moment of the examination, and you will return that to me at least or at latest in 2 hours by scanning your results or by making a photo by your phone and sending that back to my email address. Then I will print it, I will read it, I will mark it, and I will put the result into the COS, the information system. So you would be able to see the mark there. Then you will have 1 day, 1 full day, to decide whether you accept that mark or whether you want a better one. In that case, we will continue to oral examination, which would be done in Microsoft Teams. So that would yield us a good result without excess stresses, and that's all about the examination now. So in fact, you can do the examination from your home country, provided that you have a camera and a good access to internet. Is that clear and convenient? Okay, then we can switch back to electromagnetics, can't we? Let's do that. Well, so I have been talking about coaxial cables and my colleague, and I will have to make some more comments on that. A coaxial cable is a very nice thing, but sometimes you need to connect two pieces into one longer cable, and this connection is done through connectors. Those are manifold connectors. They have names like N, F, SMA, HPC, and all the connectors have to do one simple thing: to connect both connectors, the outer one and the inner one, and to fix the connection properly so it's with no resistance, and at the same time there should be no change in the characteristic impedance. We will only switch to that later, but an impedance is very important for reflections. So you have to keep the same impedance throughout the whole connection. Now this is not very simple, because in many times you have a connection that is inserting the inner conductor into a pocket in the inner conductor of the other part so that they made together. And that was the problem of the company. They have developed a connector which more or less is the outer connector of the coaxial cable. Then you have the inner connector, and then there is a hole in it, and now you cut it. This is the other part of the cable with connector that has some nuts and bolts here, and here it is like a connector which now has a rod on it, and it fixes into the inner part of the other conductor. But you know, the problem is that if you have an outer conductor and an inner conductor, that you have to support it somehow, otherwise it would not hold there. So then there was a piece of dielectrics, a cylinder, that fixes this at both sides, of course. So you have the so-called female connector and the male connector, and both have to have some bearing for those conductors to hold together. And now the problem was that they have reversely engineered a connector that has been bought, because this is quite sensitive to mechanical tolerances. So in fact, that connector could cost hundreds of dollars, for example. If that's a precise connector, it could be quite expensive. And you need thousands of those connectors to build a cable network, possibly millions of those connectors. So that's a lot of money. And now they have had a good mechanical engineer who had reversely engineered the imported, very expensive connector, and he had made something what he thought was much better for much less money. So the original solution I would put in blue, and the new solution of that company I would put in red. So the original solution was using a disc made out of Teflon, which is relative permittivity 2.2, and so you have the inner conductor, the outer conductor, and in order to decrease the effective permittivity, they make a lot of holes here. So in fact, most of this insert has been made of air. They had a low permittivity material and a lot of holes. Now, that mechanical engineer who did not know this equation decided to make something much better. So he made, again, a cylinder out of FR4, which is the material for printed circuits, with a epsilon relative equivalent to 4. And in order to make it very robust, he in fact had a two-step solution. This is the inner conductor. He put a metallic insert on that. And then there was the FR4. And as a mechanical engineer, he has seen this is a very robust solution. And there is no DC connection between those conductors, so they are insulated. So that's a good solution. And that company has believed they're mechanical engineers, so they have started production. And also this was not very cheap, so it costed something like a 1/4 of a month's salary of a good worker per piece. And they have already made 1,000 pieces. When they arrived to a problem, they started to put it into the network. It did not work. So they came to my colleague. They showed him the original connector and the new one, and it was absolutely clear what happened. We measured the reflection at that connector. It was 0.8, so 0.8 voltage has been returning back to the source, and this has devastating effect on the signal. And they have been very, very unhappy out of that. And I remember my colleague, as at that time we had no mobile phones, so we had one common phone in the room, and they have been just phoning each day. And he said, well, it's complicated. We are just making calculations. We are calculating, and they found, and we others in the room have been laughing silently when those phone calls came. But he was just laughing, and he with a stone face said, oh, well, it's a very complicated, well, possibly at the end of the week. So at the end of the week, he has sold them this equation for an amount which was just equivalent to over 1 year's salary. So this is an equation that pays off to be memorized. And what the solution was? Well, they had to abandon this metallic disc and make a lot of holes into this part, and their connectors worked, and they have produced them in thousands, and in fact connected Prague and other cities to cable networks with those connectors. But the important point, there is something which is called characteristic impedance, and you have to stick to one value in the whole network, otherwise you have problems with reflections, which is a topic we will address in a few minutes. Now please, your questions as to characteristic impedance and the equation that governs characteristic impedance in the case of a coaxial cable. Well, if there is no more question, we could proceed to another topic, which is reflection of waves at interfaces. Well, within this course, we will only address reflection of waves that are coming perpendicularly to the surface. There is much fun with other angles like Brewster's angle, polarization, zero reflection from some angles, but we will not touch that. We will only talk about perpendicularly coming wave. So now, what is the challenge to understand that? We have two materials with different properties, and there is a wave coming from one material, let's say free space, to an interface between two materials. This on the left side has epsilon 1, that right side in blue has epsilon 2. It also might be conductive, so there is a specific conductivity sigma 1 and sigma 2. And there is also magnetic behavior, so we have mu1 and mu2. Now, in order to be able to satisfy boundary conditions, do you remember from electrostatics, we have boundary conditions at an interface, and there we will have, in fact, three kinds of boundary conditions. First, boundary conditions for electric field strength and electric flux density. We already know that. Then there should be boundary condition for magnetic field intensity and magnetic flux density. We call that boundary conditions at an interface between two magnetics. And then, of course, those materials could be conductive, and then there are in operation those conditions for current density and electric field strength. But anyway, we have here a wave that comes from the media where there is some wave impedance of the first media, and there is a wave impedance of the second media. Now those generally are different, which means that the ratio between field strength, electric field strength, and magnetic field intensity is different here and here, because those values are different. And that means that you can never satisfy this condition with only two waves, I mean incoming from here and protruding through the second environment. You would need three waves. So in reality, unless those two materials do have the same wave impedances, there should be a wave that is coming. Now I mark the pointing vector direction. This wave should have the index 0. So it has E0, H0, and of course pointing vector S0. And then there is a wave which is reflected back from the interface. This we would call E1, and of course it would have H1 and S1. And then there is the wave that is propagating, that makes it through the interface to the other material, and that would have E2, H2, and S2. Now it must hold that the tangential components of electric field strength are identical, which means that E0 plus E1 are just equivalent E2 at the interface. For magnetic field, that must hold that also H0 plus H1 is H2. This is because all those components are tangential, as the electromagnetic field of that wave is perpendicular to the direction of propagation. So the tangential components must be the same at both sides of the interface, as, let's say, field strength and magnetic field intensity. And if you put this into a set of equations, you will get a solution. That solution uses something which we call reflection and transmission coefficient. A reflection coefficient R is a ratio between the reflected wave and the incoming wave at the interface. So it's a ratio between E1 divided by E0. To be exact, we should put down that both those two ones are phasors, so that in reality the reflection coefficient could be a complex number. And now this would be equivalent to a ratio between this ratio, the reflection coefficient, is given by the wave impedances of those two media. Now we also have a transmission coefficient which expresses the ratio between the wave propagating into the second media and the wave incoming to the interface. So it is E2 over E0. Again, we should mark those as phasors. That means that transmission coefficient is generally a complex number. And this coefficient, again, is given by an equation, and it is 2 times impedance of the second media divided by a sum of the impedance of the first media and the second media. So given this into account, we are able to specify the values of electric and magnetic fields of both waves that emerge at the interface. So there is one incoming wave, the black one, and there is a reflected wave and a wave propagated to the second media, and both of them are determined by those two equations, so that you can find out the result of this situation as to magnitudes and phases of those two waves. Now, I would like to make an example, which will be then followed by after some consideration on material properties. So first an example. Let's consider that we have an interface between two materials. The first is vacuum, free space. The second is a kind of light glass, let's say with a relative permittivity of 4. So let's consider how much of electric field strength reflects back. What is the value of the reflection coefficient? And let us consider how much energy reflects back from such an interface. So an example, we have an interface, both media are non-magnetic, non-conductive. Here we have vacuum, here we have something like a light glass with a relative permittivity of 4. Now let us express wave impedances of both media. So for vacuum, we already know that this is 120 pi. Ohms. For the other media, we have to resort to the equation which says generally that the impedance is equivalent to J omega mu over J omega epsilon plus sigma. We fortunately have no conductivity here, so in fact if this is 120 pi for vacuum, then if we have permittivity 4 times higher over here than in this case, this second value must be a square root of 4 times less, which would be 60 pi ohms. And now we can express refraction coefficient. We have the equation here, so let's rewrite that. Our reflection coefficient on the interface would be 60 minus 120 pi's divided by 60 pi plus 120 pi, which is easily recognized as minus 1/3. So 1/3 of the field strength reflects back in this case. How much that does give to the power? Well, power is expressed by Poynting vector, and we can, in lossless media, take into account that the Poynting vector, which is E times H, then we will have E times E divided by the impedance of the media, which for a lossless media could be rewritten like E squared divided by eta. I would put here only not equivalence but proportion, because we would have to discuss this for phasors a little bit later. But anyway, this is the proportional principle, so it is proportional to E squared divided by the wave impedance. Now, if the reflection is 1/3 in E squared, so if the reflection of E is 1/3 and the wave power is proportional to E squared, it is easily seen that S1, which is the reflected power divided by the incoming power, must be 1/3 raised to second power, which is approximately 11%. Now this might be quite surprising. In most cases the permittivity of glass is slightly over 4, the relative permittivity, and this conclusion tells us that 11% of light is reflected back from a window, or better said, it's reflected back if that was only a transition between the air and the glass. But in an average window today we have 2 glasses, which means that there is the transition from the air to the glass, from the glass to the air, from the air to the glass, and from the glass to the air again. And then we can easily lose half of the power of the incoming wave. And surprisingly, we do not feel that. If you look out of the window for your side, it's transparent. You don't see the big difference in the power that would be there without the glass. This is because human's eye works logarithmically. It's prepared to have big differences between the exposition at direct sunlight and, for example, at night, so that you do not feel an increase which is just 1/2. That's not a difference that you would see by your eye normally. So the situation is that our window filters a lot of incoming power, reflects back, but we do not sense it by our eyes. Of course, if the glass is extremely dirty, we can see that, but then the reflection or the transmission are quite different. Your questions, please. Well, if there are no questions, I would like to continue and talk a little bit about the nature of those numbers we input into our calculations. I mean, we have been using properties like permittivity, permeability, and specific conductivity out of those three values, we are able to obtain propagation constant, which means we are able to get depth of penetration and wavelength. And we are also able to get impedance. And impedance is then related to reflections and transmissions at boundaries or interfaces. Now,